Welcome to AP Physics Podcast. This is Chapter 15, homework number 2. We're going to start with question number 12 today. We have a 1 kilogram glider which is attached to a spring that has a force constant of 25 newtons per meter. And with this object, it's oscillating on a horizontal frictionless air track. We know that it's released from rest. That's a big important thing at x equals -3 centimeters. So we're trying to find the period of the motion. We have an equation for this. That period is equal to 2 pi times the square root of m over k. So if we just plug those things in, we know those various things. 2 pi times the square root, our mass is 1 kilogram, and our k is 25. So if we do that, we get 2 pi times 1 over 25. Oops, 1 over 25, not 2 pi. And when you work that out, you get 1.26 seconds. Now the other way that we could have found this is we know that period relates to angular frequency by this, 2 pi over omega. And omega, really, our definition is it's the square root of k over f. So if you use that, you do the same thing down here. Those are very similar. You end up plugging in that 25 over here, so we get omega is equal to 5 radians per second, which is going to be quite useful. And then you plug that in over here for t, and you end up getting the same thing, 1.26 seconds. So it takes 1.26 seconds to go back and forth once. We're looking also next for the maximum values of speed and acceleration. Remember, in our general solutions, that x is equal to a times the sine of omega t plus v, and then that v is equal to a times omega times the cosine of omega t plus v, and there's a negative sign out front here. And then for our acceleration, a is negative a omega squared times the sine of omega t plus v, or you can change these to cosine, however you want to do it. Although I'm just realizing that this negative sign should not be here. It does not show up until right here if we start with sine. The point of all that mumbling was that we find that the coefficients in front of v and in front of a, in front of our functions, are these values right here. And so this is a general thing that we can look at. Our v maximum occurs at the value a omega, and our a maximum occurs at the value a omega squared. And since we just found omega here, and we know that a is 3 centimeters, we end up getting 15 centimeters per second, or 0.15 meters per second. And then the same thing for our a, we get 75 centimeters per second squared, which is 0.75 meters per second squared. So then as we look for the position, velocity, and acceleration functions as a function of time, we can just plug them into our equations. We get that x is equal to a. Our a is 3 centimeters. So we're going to have, but we're starting at -3, so -3 times the cosine of 5t. In this case, 5 is my omega. I didn't put any phase shift in here because we are released from rest at x equals 3 centimeters. So that means that we need to start at 3 centimeters. At t equals 0, we need to start at -3 centimeters. So if we verify that at t equals 0, that means that x is equal to -3 centimeters. So that's a good thing. Our v function is going to be a times omega, so that is going to be, let's see, but negative, so negative a times negative omega. We end up getting 15 times the sine of 5t, and we can get that also by taking the derivative of our x function. And if we verify that, that means that t equals 0, our v equals 0, which is not very helpful to us. But we can then see that at a maximum, we're left with 15 centimeters per second. And similarly for a, if we take the derivative of this, dv dt, we get the same thing, 75 cosine of 5t. And now it's probably a good idea for us to write our units in. So for up here we have units of centimeters, here we have units of centimeters per second, and here we have units of centimeters per second squared. This is question number 12 from AP Physics, Chapter 15, homework number 2.